Okay, let's try an ice example. So this problem says, if you can solve equilibrium problems with chemicals, you can do it with random letters too. I'm sure that sometimes chemical reactions seem like random letters to most of you anyway. So let's try this not quite a chemical reaction. So the reaction we've got is A is in equilibrium with B plus 2C. And the phase symbols on all of these are aqueous, so they're all concentrations. And we're given the K. K is 1.3 times 10 to the negative 7th. So if you begin the reaction with 0.30 molar A, what will be the concentrations of A, B, and C when the reaction reaches equilibrium? All right, so this is a classic ice problem. So we look at the chemicals in the reaction, and we see that all three of them are aqueous, so all three of them are concentrations, and all three of them will show up in the K equation. So our ice table has to include all three. So we'll have A, B, and C on our ice table. And initially, it's our I, initial, A is 0.30 molar. And the whole table is going to be in molar, so I'm not going to write M's all over the place for now. All right. We're also starting with B at 0 because we haven't added any B and we haven't added any C. So C is at 0. So those are our initial concentrations. Now during the reaction, there's going to be some change. So we've got stuff on the reactant side and nothing on the product side. So it's definitely going to shift to the right. So A is going to go down by some amount, and B is going to go up by some amount, and C is going to go up by some amount. But look, C has a stoichiometric coefficient of 2. So if A goes down by 1x and B goes up by 1x, C is going to go up by 2x because of the stoichiometric coefficient of 2. So really, you just put the stoichiometric coefficient in front of the x. All right, so at equilibrium, the E of our ice, we just have to do a little math here. This is 0.3 minus x. This is just 0 plus x, which is x, and 0 plus 2x, which is 2x. So there's my ice table. I have expressions now for all of the concentrations at equilibrium. And if I only knew what x was, I'd know the concentration of everything at equilibrium. But I don't know what x is, so I have to plug it into the equation for K. So the equation for K, as always, is products over reactants, all raised to their stoichiometric coefficients. So it's products over reactants, all raised to their stoichiometric coefficients. Well, A and B have stoichiometric coefficients of 1, but C has a stoichiometric coefficient of 2, so I have to put that 2 in there. All right, so now I plug in my equilibrium expressions. Well, at equilibrium, B is x, so I'll put in x for B. At equilibrium, C is 2x, so I'll put in 2x for C. And remember, this is squared because it's all raised to their stoichiometric coefficients. And we're going to put this over the concentration of A, which is 0.3 minus x. Now, we always start by trying to make things easy. So let us start with the assumption that 0.3 minus x is essentially just 0.3. We'll check this after we work the problem, but for now, let's try the assumption and hope that we can get away with making this an easy problem. So that means K is equal to, so if I take this top, 2x squared is 4x, 4x times x is 4x cubed, so that's the top. And the bottom now is just 0.3. So I multiply both sides by 0.3. So 0.3 times whatever the K number is equals 4x cubed. And that means that x cubed is just going to equal 0.3 times K. I'm going to have to put K in here. 1.3 times 10 to the negative 7th over 4. I had to divide both sides by 4. All right, so let's work this out. X cubed is, all right, I'll put this in my calculator. And boy, is that a small number. So here's what my calculator said it was. 9.75 times 10 to the negative 9th. Boy, that's a tiny number. But that's okay. My calculator is perfectly capable of taking the cube root of that, because x now has to equal the cube root of that number. So I put that into my calculator. On mine, I have a key that looks sort of like this. That does multiple roots. I have to hit the key, the 3 key, then that key, then I hit 9.75 times 10 to the negative 9th. And it'll give me the cube root. So I did that, and what I got for x was 0.0021. And I look at that, and I see that I only have 2 sig figs, and to 2 sig figs, 0.3 minus this is just 0.3. So my assumption is perfectly good. Yay, my assumption is okay. Now, though, I want to know what the concentrations actually are. We don't stop when we get x. We use x to figure out this row of concentrations. So the concentration of A is 0.3 minus x, but we just decided that that's essentially 0.3 to the 2 significant figures that we have. So we're just going to leave that as 0.3 molar. B is just equal to x at equilibrium, and so that's just 0.0021 molar. And then C, because it had that stoichiometric coefficient of 2, is equal to 2x. So I pop this into my calculator, and I figure out that this is 0.0042 molar. And there we go. Those are the concentrations of everything at equilibrium.